Esperar el que fue por el café. Well, we can
Okay.
go ahead and
No, no.
introduce. We can start or. Oh. Oh, he's back. Okay, we can start. Yeah. No, don't. Just nervous. Yeah, let's go.
Let us continue with the second talk. So it's my pleasure to present William Vickery from
Peking University.
From Peking University, yes, very far. So, yes. Who will talk about a parabolic Anderson model with colored noise in the torus.
Thank you very much for the introduction. Thank you, everyone, for being here. I'm very new to the community, and so I'm very happy to meet the people here. I was joking with Vilker last night that we could spend the whole talk reminiscing with anecdotes of what a great guy he is, and I could sort of run out the time that way. But so instead of doing that at the beginning, we'll do that at the end. If we run out of time, then we're going to go over to the humorous anecdotes. So I gave a version of this presentation in Mérida before, and I received some feedback. Sometimes we call it criticism. I think criticism is a good thing. I hope that you criticize my presentation so I can improve. I tried to address some of the questions that arose within the talk, so I hope new questions will arise and more development of the ideas can occur. So this is the problem that we have, which is the stochastic heat equation. And the derivative of the idea is that we're going to add this random variable here. This is going to be a kind of distribution, but that is randomly generated. And it's not going to be integrable using classical methods. And this is sort of a theory that developed outside of the world of math physics about how to integrate these random processes and get answers. So doing the sort of, this is one of the kind of big names in the field from SUNY, the SUNY system in New York is Kosh-Navison, and he generated these simulations using finite mesh. This is for a deterministic solution, which would correspond to lambda lambda equals 0. Then we're here with small lambda, 0.1, and you begin to see some ripples of the noise. You have to keep in mind that this noise has a feedback term. So you are multiplying the value of the function times the noise, and that's being added to the derivative that's going to make it increase. So when lambda equals 2 increases, you start to get very high peaks that are kind of separated. And when lambda equals 5, these peaks can even approach values like 10 to the 19, which is quite large indeed. So this feedback effect is very strong. It's very interesting. People want to know about it. And the way that they study it is with these Lyapunov moment exponents. So you take the function here, you take u, and you take the expectation value of p, u to the p, that's the pth moment, and you take the logarithm, and you divide it by t. And you can take the lim sup or the lim inf, but we're sort of working in a context where we're going to, because everything's linear, we can just take a limit. We're going to prove that later, of course. So the idea is that when you have this Lyapunov exponent, the pth moment is growing approximately e to the gamma pt. So this is exponential growth in the moments. And when you have these moments, they're always increasing. So you're always going to have this less than or equal to, which can be proved with Holder's inequality. So if you go through a quick calculation, you can see that it's possible to show this, the increasing part. And strictly increasing is what we want to prove. This is going to give us this behavior that I'm about to describe probabilistically. So if you have this event here, let's say u of t comma x is bigger. Well, let me go back. This is without dividing by p and without dividing by t. We're going to look at this convenient thing. It's a new variable. I always hate to introduce too many variables. It causes me a lot of anxiety when I'm generating these presentations. But this is the log of the moment. It's not divided by t. And so it's something that's a function of t. And if we interpolate between these moments, if there's a number here that we can pick out because it's a continuous interval, then we can ask about this question: what is the probability that u of t comma x is bigger than e to the lp of t? So we can do Chebyshev, which is for the pth moment, u to the p, and then we're going to multiply it by e to the negative p lp of t. And this here is e lp of t. And this is a strictly bigger number that's more negative. So this, and remember, this is sort of like gamma p to the t, and this is sort of like gamma p to the t. So this is e to the negative positive times t. So that's going to go rapidly to 0. So this is a very small probability event. And that that corresponds to the measure in the probability space, which is not the same as this actual measure in squares. But we're going to get to that in a minute. So on the other hand, we have the question about what is the measure of the complement here. So what about if u of t comma x is less than this number? So we want to measure how much of the function's mass is supported in the complement where u is small. So now this is an expectation that's over the probability space again. So this is for a fixed x. But if u of p is small, what's the value of this? So if we don't have a really high peak, is the idea, what is the expectation of u of p t comma x to the p plus 1? So we apply this inequality here, which is that basically u is going to be less than e to the lp on this set, this complement. So we continue, then we can kind of add back this constant lp plus 1 of t. So this is going to be negative here. And now we're seeing that the fraction of this fraction is going to go to 0. And so this is the moment of u of t comma x to the p plus 1. So that's if we integrate over all the possibilities, at a point, the pth moment. This is going to be a number that's actually quite large. And this number here, this is the p plus 1 moment, but if we ignore the peaks, if we ignore those events where you've gotten exponentially large. So this is going to be comparatively small. So this is suggesting that at a fixed x, so we don't have anything that's giving us these islands of high peaks. We don't have that yet. But it's telling us that for a fixed x, you're either going to be very, very small or very, very large, which is the motivation when you're working over the finite for why we talk about this intermittency and the probability. So when people are working, so this is an aspiration for a way to deal with it that they end up doing in the finite case. So the idea is that if we write this process as a Hamiltonian, we can write the solution as a semi-group evolution. Pedro, my new colleague, was just explaining to me this in the EMAS office the other day. We were working on the whiteboard. It was a great feeling. And this here, this is going to be, so you're going to get these exponents in time, which will give us the kind of evolution we're looking for. And then you're going to have these eigenvectors. And what they proved in the finite case is that these eigenvectors have very small support. So this book here by Koenig is a review of mostly the discrete case for the parabolic Anderson model on ZD. And this is the paper that introduced it, but it's a little bit difficult to read. I would recommend this book. It's very readable. So in order to get their results, they make a lot of assumptions. There's a lot of assumptions on the noise has some limits on it. The solution now is going to be inside of a box. And the idea is that for certain class of random potentials, so you can't deal with just anything yet. And it's not relevant to go into the restrictions right now because they're very probabilistic. For a certain class of random potentials, we can pick this sequence RL. So RL can go very slowly to infinity. But what we can find is that there's going to be this sequence of random variables ZK that are going to be the centers of these islands. And these are orthonormal vectors. So that most of the mass is going to be close to these random variables ZK that are just like, it's like you can, and they also prove that these random variables can be a Poisson process, that they sort of pop up and then you have a little ball around them of radius RL. And then for any of these eigenvectors, most of the mass is going to stay around these centers, but the centers are also random variables. And so RL is also going to infinity, but you can choose it to go very slowly so that as you increase this box, you can kind of make the box arbitrarily big and keep RL very, very small. So the question is how to deal with this for like a PDE that's driven by a stochastic noise. And there's a lot of theoretical foundation to just define the solution, which I'm going to introduce now. The Ito integral is a way to integrate an ODE that's driven by a Brownian motion. So the idea is that sort of like when you have this Young integral. Let's see, is there any chalk in the... Well, we don't have to go crazy and improvise. Is there chalk? Is there any chalk? It's in this thing here. It's in the desk. Oh, here we go. Okay, thank you. Okay, lots of chalk. Thanks. So you can define an integral like this, f dg, for a deterministic function g. And you have to have that the f, the p variation of f, and the q variation of g. And so the idea here is you're going to have something like f of x I g of tk plus 1 minus g of tk. So instead of using just time as an increment, you're going to use this function's value as the increment. And the function can be very oscillatory. It can even be negative, but it can't be too oscillatory. So the Holder norm, the Holder norm, the p variation norm is just 1 over the Holder norm. And you need 1 over p plus 1 over q is greater than 1. So in particular for Brownian motion, the Holder norm is 1/2, and it's not possible to get this to work even for a bounded variation function. So you have to go to this stochastic theory, and this integral. You could think of this like a Brownian motion, and you define the solution here by saying that we're going to integrate this limited class of functions, these indicator functions, for just a short interval of time, and this xi, which is a special random variable that's measurable with respect to the sigma field generated by Ti. So this allows you to use this this space of functions to start with these functions and then define the whole integral. Basically, you have a SDE here with this random variable that's driving it, and you change it into an integral equation. So we've defined this integral against the noise, and then we have an implicit definition for the solution. So to do this for a PDE, now you have to have a measure that's indexed by time. And the measure here is this is going to be the martingale T. And then for fixed T, it's going to be a L2 of P random measure. So it has to be measurable with respect to the probability space. And you have to always kind of keep, so you're going to get a set A in your actual space, and that's going to give you a random variable that's on omega, which is this space of random kind of indexes, and it has to be L2 in omega. So you always kind of have to keep track of when you're working over the Rn and when you're working over the actual expectation value integrals. So you do the same thing. And then, so white noise, for instance, this is going to be a random variable that's Gaussian. So all you have to do with the Gaussian random variable is define the covariance and the mean. So the mean is going to be 0. So it's average 0. And then if you have this this covariance, two sets A and B, then you want to look at the covariance of those two Gaussians as when you plug these sets in, you're going to get just two regular Gaussians, like a normal curve. And then the covariance is going to be the measure of the intersection of those two sets. So it's sort of it's how much it's oscillating up and down. The variance, the width of the normal curve is going to be the measure of the intersection of the sets. So then you can integrate these processes according to starting with indicator functions again. You start with indicator functions, and then you sort of do the natural thing, which is that this is like a fixed, it's like a constant basically, that's constant on these sets. And then you integrate but the random part comes from the constant weight on these indicator functions. And then so you take the weight and now you multiply it by the process, just defined very simply on these rectangles. And then you can take the limits of these things in the appropriate space, that would be good to specify. But the idea is that you can take limits of these things, and you have this isometry called the Ito-Walsh isometry. That's the norm on your space, and you can show the norm is conserved before and after. So these limits are preserved, and sort of figuring out what's inside of your space is a part of the job. So this is how we express the heat equation using this integral. And so it's an implicit equation where it appears inside the integral here. And this is the Ito-Walsh isometry. So what we can do is we can move the expectation inside of the integral, and then we're going to replace the noise with this function that kind of defines the covariance of the noise. And so this function is singular. This is singular at 0. It's going to go to infinity at 0. And how fast it goes to infinity is going to be controlled by alpha. And we'll get into that in a minute. But the idea here is that if you have y and y prime are the same, then but it's going to be integrable anyway. So it's sort of a weight. It's a weight that is heaviest when y equals y prime. It's infinite when y equals y prime, but it's all going to be integrable overall because the alpha can't get too small. And some of the more advanced work in this field is dealing with more singular correlations. So this is how we define our noise. This is the same thing basically. You have a Gaussian random variable and you need to define the covariance. So in this case, we are looking less. These functions here, you can think of them as like C infinity compact support approximations of indicator functions. And now the product of this inner product on the Hilbert space of these functions on L2 of the torus, this inner product that we're defining, that's going to give us the probabilistic structure on them. And analogously, there is a way to think of this as a measure of a set. If you compared it to the white noise case, this is going to give you the inner product of two bumps that are approximating the sets. And this inner product is over the Fourier space, but it's going to be convoluting the two indicator functions. So it's kind of softening everything. So this is the heat kernel on the torus that is going to be a part of the equation and a part of sort of even the definition of the noise. It starts very singular, supported at one point, and as time goes forward, it spreads to become a constant function, but non-zero critically. And just to comment again, if we had white noise here, alpha would be 0. So the inner product of the two functions would just be the Fourier, the Plancherel theorem would tell you that this product, the coefficients of the Fourier series will give you the L2 product of those things. So the L2 product of two indicator sets gives you the measure of the intersection. So this is everything sort of softened from that L2 product. And this is how we produce a function that has the desired Fourier series that we want, this divide by k to the alpha. And the noise correlation function, if you have rho equals 0, this rho is important to us because if you have rho equals 0, then the integral of this function is 0. So it's going to assume positive and negative values. And that's going to cause some problems for us that we'll fix by having rho increase. So rho is going to be bounded below by this function here that gives a lower bound on the most negative values you can have for the correlation. And theta is a constant that should be on the, theta comes from upper bounds on how the Gaussian can grow in time. How big can it be in time? So the Fourier coefficients are 1 over n to the 2 alpha. And this is going to give us the kind of, this is why it's called the colored noise, because if you look at it on sort of a spectrum analyzer or a waterfall function, you know, maybe that you might see in some music software, it's going to, instead of being just one line, it's going to kind of soften off at infinity for the spectral decomposition. So this operator was developed by my collaborator Le Chen in his thesis work. And this is using the heat equation, basically it's how you update the heat equation with this noise correlation product taken into account. So these two functions, you're convoluting them in time and taking the product in space where it's weighted by this correlation. And now we're going to define this series Ln that eventually is going to be helpful for our solution. So this is how we're going to express the solution in terms of Ln, that it's going to be the initial condition, and then we are going to have this weight that comes out, L squared, from the parabolic Anderson model, that coefficient. Then it's going to be Ln is you put that into the initial condition. So you have to incorporate the initial conditions to the solution. So these are a few of the terms here just to kind of get a sense of what's going on. And so yeah, I'm going to go back to this in a second. The goal of here would be to write Ln as a linear operator, and then it's going to be in the form that we want, and then we can find the eigenvectors and we can find the eigenvalues. And part of the if you think about it, this time integral that keeps coming up, we keep having to repeatedly integrate with time, and that is going to give us this dividing by n factorial and having t to the n. And if we can get ln in the form a t to the n over n factorial, then it's going to fit nicely into the functional calculus. So if anybody has any suggestions for how to do this, I would appreciate it, of course. And now we'll talk a little bit more about the nitty-gritty part of it. So this is L0. This is just the heat kernel, kind of two variable heat kernel. L1, if you look at what's happening here, we start at time 0. We go to time s. We arrive at time s. And now we're sampling starting at time 0, where could we be? Where is Z possibly? Because we had S seconds running this diffusion, and then we arrived at Z. And this one arrived from X0 prime to Z prime. But the idea is that there's a diffusion from 0 to S, and what's the probability distribution that we're at some Z after S seconds? And then we have another diffusion that's going to run from S to T, so it's going to run for T minus S seconds. And then the idea is we're starting at Z, and we're gonna get to X here because X is an input. But when we look at more terms, it's kind of like you can write it like this, that you're running from S seconds, run the diffusion, arrive at Z1, then you're at S1, you're going to run the diffusion for S0 minus S1 seconds, and you're going to get to T minus S0. Then you're going to get to run it for S0 minus S1 seconds, get to S1, right? And then we want to get to T, so we're going to run it for T minus S0 seconds. And each one we're sort of hopping from one position to another. So as n increases, there's sort of a process here that is given a suggestion here, and but each of these processes, you're looking at the correlation function on the difference of these two processes. So how can you linearize this thing? Just taking the Taylor series and linearizing it might be naive, but if you can think of the operator to be kind of an elegant key to this lock, then that would be pretty good. So Romain Ale and Khalil Chok, they had a 2015 paper where they try to describe the eigenvectors and the Anderson localization on the torus for the white noise case. So they produced that with very very analytic estimates. I don't think they used the method I was just suggesting of decomposing this other operator. And then Martin Hare and Cyril Labbe are Cyril Labbe was Martin Hare's postdoc, and they wrote two papers the same year where they solved the continuum parabolic Anderson model on R2, but they didn't have to use the renormalization. And then in R3 they used the advanced modern methods that are a little bit opaque, very difficult to learn, that use renormalization along with these spaces that are like Bezov space and things like this. So what was suggested when I was doing my research for my thesis about the question of how to deal with this operator is that the process that occurs at each step, where you're going first from 0 to S, then from 0 to T, and you're going first from X0 to Z, then you're going from Z to X. That's called a pinned Brownian motion. And if you run it for the variables are S and Z, so you're sort of looking at in the middle. If you've run this Brownian motion, that you know where it ends up and you know where it begins, what happens in the middle. So this is related sort of to how we had this process appearing in the Picard iterations of the density appearing with little tiny increments. So to bound so far the application is only to just bound the Picard iterations and show the convergence. But it's suggestive that there's some kind of logic here that we could develop eventually. And I invite anyone with any kind of brilliant ideas, please, to just shout them at me. Why didn't you think of this? I'm interested. But so the idea is that now this denominator here, this can be pulled out in front, and the denominator becomes not dependent on the integral variables. So this is now sort of outside of the integral, and now we can just deal with, instead of dealing with two Gaussians and bounding them separately, now we have one Gaussian, because this is also a Gaussian random variable with a formula in terms of Gaussians that are simple Gaussians. So this is the conclusion we're going to arrive at. We're going to sum up these LNs, which are highly suggestive of the linear functional analytic theory, and we're going to bound it by just Cn t to the n by bounding the pin Brownian motion. And so how are we doing on the time here? What time do we start? 10:10. Okay, great. So this condition is from the classical methods for solving the stochastic partial differential equation on Rn, which is that the Fourier transform of the noise, the singularities can't be too large. So you have to have an integrable Fourier transform. So in this case, it's an integrable Fourier series, and we're gonna sum over ZD k, and the sum is gonna be exponentiated by 2 alpha plus 2. So reminding that if you're in ZD, this has to be bigger than D, right? So 2 times 0 plus 2. So for k, the sum over k squared, that's not going to converge except in dimension d equals 1 for the white noise. So what Cyril and Martin Hare did was pretty clever, because they pushed this limit past what DeLange had done before, but without using the modern methods. But so for us, we can get something that converges in kind of arbitrary dimension, which is kind of a nice part of it, because you can make alpha bigger to get something to work. So this is the noise again, and this is how we're going to bound our process. We're going to bound it with this integral hn of t, which at each step you're integrating a bound, two separate bounds on the increment, on this Brownian bridge. This k1 is going to be a bound on the Brownian bridge for small time, and k2 is going to be a bound on the Brownian bridge for larger times, because of the torus. It's very similar to the kind of Dirac delta function on Rn for a small time, and then it becomes a constant function. It's much easier to bound for larger times. So, and this is also not the function. This is an upper bound on the function that has a convolutional structure, sort of a semi-group structure. But so this here, we're going to let t be bigger than epsilon, and we only have to deal with small t less than the time, because it's symmetric. You can just flip it. So this here, we're going to bound G bar, the pin Brownian motion, with two Gaussians. And it's pretty straightforward how to do this. You just sort of use the formula. Yes, a question.
Can you write explicitly what is the G, the capital G, the definition of this capital G? And,
Yeah.
And where do they come from also? How do they appear?
So G on Rn is going to be, on R1 is going to be root 2 pi t e to the negative x squared over 2t. So this is the fundamental solution for the heat equation on R. And the idea for the torus is that the torus is R mod r mod 2 pi, r mod negative plus or minus k pi for odd k. So if we want to have the same integral, if we want to integrate g bar of t comma x comma y times f of t comma x comma y on t2, we want that to be equal to the integral over r over t of the fundamental solution times f extended to the same points. Okay, this is g of t x, and this only has one, f of t comma x, because x, g of t comma x comma y, this is x minus y squared. So the idea is that it's for a heat kernel, it's like a diffusion process that starts at x and ends at y. Then the distribution is going to be x, or you could say y minus x if you want to, but it's the same under the squared. So the idea is that we want this thing integrate over the torus. We want to get the same behavior for the function that is defined to be the same on the integral classes. So we need to make g bar be equal to g bar is equal to the sum over k in z of g of t comma x plus 2 pi k comma y. So the idea is that in this case, if we're dealing with a function, if we're dealing with the point y, we want a diffusion that could start with any of the representatives of x. And then if you have this, the sum over k and z of the integral from negative pi to pi of g of t comma x plus 2 pi k comma y f of t comma x dx, that's gonna be equal to the integral over r of g of t comma x comma y f of t comma x dx. So the formulas that hold over r are also going to hold over the torus if we define this this to be the g bar. Okay. So in the case here of large T, then we have upper and lower. So basically, if T is large, we can ignore this because it's going to have a lower bound. So if T is large, then we have, because then the Gaussian is going to be lower bounded everywhere. So we can just get rid of the denominator, and then we can use the smaller Gaussian, which ran for time s, and then t minus s is going to be bigger. So the smaller Gaussian is the only one that's going to be contributing to the lower and upper bounds. So that gives us a very convenient formula, which is now instead of so here we can replace the pin Brownian motions that we put in here with regular Gaussians as upper bounds. And then this product here, if you integrate this over space, that gives us our inner product. And we had a Plancherel formula for the inner product. So this is already an upper bound on L1. So this gives us rho hat, and we want to increase. In this case, we don't actually need to increase rho hat, but later we're going to increase rho hat to make the correlation positive. But in this case, we are going to get this formula for an upper bound on this integrand. And then, so we're going to define that to be K1 of S, which is going to be for large time. So e to the negative S, K squared over K to the 2 alpha. If this converges, if you integrate this with respect to S, you're going to get another 2 alpha plus 2 in the denominator. So now the t less than epsilon case is more complicated. And as basically what we want to do is work over R. After we have after we make t small, the Gaussian is going to be all concentrated at one point. And so now we want to try to represent this process as a process on R, and then it's all going to be very close to the origin, and the past results for the bounds on R, solving the equation on R, will be applicable to the torus. So we have to keep in mind that so this x0 point here, it can be it has a lot of variability, because the base point, once you have many of these for the higher order terms, the base point is going to be different each time. So you could get in a situation where x0 is here, and then x is here, and then you're getting this pin Brownian motions probability is non-zero over here at z. So at the point you're measuring it at, you could still have a substantial mass here of probability. So what's safer for when we make this branch cut and we're no longer representing things on z, is that we have to include another base point for the Brownian motion, the pin Brownian motion at x tilde on the mirror point, so that if there's any kind of issue, which you might find here, so this is if the distribution is perfectly centered, you'll be okay. But if the distribution is overlapping the branch cut, we want to try to make sure that we deal with that by mirroring everything on both sides of the branch cut. So now we are increasing the number of integrands. Now x star here in this pin Brownian motion is going to be either x or the mirror point x tilde. So that's going to be 4 terms, but luckily it's finite. And now f alpha rho, we increased rho hat here to make f alpha rho positive, so that we can make this analysis easier. And f alpha rho has a singularity at 0. And so on the torus, there's going to be a little bit extra mass. If you look at a point and you represent it close to negative pi, then that we have to have another representation of the singularity that is giving the appropriate mass that comes from overlapping. And because we're going to want to bound our noise above with x to the negative d plus 2 alpha. And this is this is constructed to have the necessary Fourier transform that we're looking for. And this is going to be, and if you add in the mirror points, this will be an upper bound for the extension of f alpha comma rho hat. So this on R, if we extend f alpha hat comma rho hat to R, this is going to be an upper bound. So the final part is to convert the pin Brownian motion back to being a Gaussian, because it is a Gaussian random variable and there's an explicit formula for it. And then what we can do now is we've upper bounded everything, and we're going to put it into, we're going to express it as a Fourier, we're going to express it as a Fourier series. So this is from the Fourier series representation of the pin Brownian motion. This is from the Gaussian. This is we're working in Fourier mode, and the Fourier transform of the Ries kernel times, this is from this is to represent it as it only has one term. Yeah, this is the Fourier, this is the actual Ries kernel, and this is the Brownian motion. But essentially this is the one of the more technically involved steps, so we don't have to go through all of it. This is the upper bound we're going to get, which we're going to have e to the negative st minus s times psi squared, and this term here, this is going to converge the which integrand? The inequality is, this should be positive. This is positive here. Where would the absolute values go? Inside the integrand? I forgot this step, but I think what we're doing is just doing a Plancherel thing where we're computing, because we have to bound this. The technical details are escaping me at this moment, but if you trust me that it's gonna go from this thing down to this thing that's a little bit simpler, then eventually what we'll get is that that we can put K2 of S, we integrate K2 of S from 0 to infinity. It's going to get us to this bound here, which is psi 2 alpha plus 2, and this is the DeLange condition that was the end point of the roadmap. So some of the technical details are escaping me at this exact moment, but if you trust me on that, we can go over it and check it all in detail afterwards. So this is an upper bound now on this theorem, on this this function that we want to try to make more explicit and physical eventually. And this is the attempts that we made for the Lyapunov exponents. So we wanted to show strict increasing, and it's sort of it's a fact that if you have gamma p plus 1, if you show that it's increasing for any of them, you can show it's increasing for all the higher order terms. So if we gamma 1, also you kind of take for granted that it's equal to 0, and then if gamma 2 is greater than 0, that will show the whole thing is increasing. So we just work with gamma 2 and we try to show it's greater than 0. So the first attempt is to do what we did before, where we increase rho. When you're doing a lower bound, you can't increase rho and get another lower bound. But what you can do is, if you assume rho is bigger than the value that's the lower bound on F alpha, you can assume the kernel's positive. And in that case, you have a very easy lower bound. That becomes and this lower bound here becomes an exponential lower bound. What they do in the finite case and what we did here with some attempts is to use this Feynman-Koch formula. And the Feynman-Koch formula allows you to if you look at this integrand here, you're taking an integral over space, right? Taking an integral over time. So let's look at the integral over time and let's divide it by t. Well, the idea of an ergodic function is that this is going to go to the space average. And the space average is just going to be rho over 2 pi to the d. And the F alpha part, the part from alpha with rho equals 0, that's going to be 0. So this is telling us that we are going to get exponential. So this can all become e to the rho t if we put the t on this side. So this is strongly suggesting that we're only going to get this intermittency if rho is positive, and that if rho is 0, this is going to go to 0, and we're not going to have an exponential lower bound. And so what we do is we prove that if rho is positive, this is the proof that if rho is positive, we will get the exponential lower bound. Let's apply the Jensen's inequality. So we just are dealing with this integral. And this now, F alpha rho, B2S, this is going to, we put this in the Fourier series representation for F alpha rho. Now to calculate the expectation of this term, we made a teeny little boo-boo. We forgot this equal sign in Merida. But so now it should be corrected. E to the I n times x, and then multiplied times the distribution at time 2s, and you integrate that over the whole torus, and that will give you that's the definition of the expectation of this random variable. So that is equivalent to the Fourier transform. And when you calculate the Fourier transform of this Gaussian, it's going to give you e to the negative s n squared. So then we calculate the expectation now of this. It's going to give us the rho t that we predicted from the ergodic behavior, and it's going to have on this side, we're going to be summing up n to the negative 2 alpha from the noise definition times the integral e to the negative s n squared from the kernel. So that is going to be, when we integrate that, it's going to give us another n squared coming out, and it's going to be the sum of n to the negative 2 alpha minus 2. And it's going to be, now it's going to be times this. So this is going to be bigger than a constant, but it doesn't have we need a constant times. Oh, well, this is going to be, so this equal sign is a mistake. Rho t here, this is going to give us the exponential lower bound. This part here is equal to this here, and that is a constant. So if we have rho equals 0, then if this sum converges, it's not going to be intermittent. But if this alpha if the sum doesn't converge on the critical case, then it's possible we could get the intermittent back because we don't get the lower bound anymore. But this for rho is greater than 0, sort of juicing our noise with a little extra oomph, we get the intermittency. So as I said, I responded to the feedback from Merida, and I hope that you can share some more. Thank you to Miguel, to Luis, who I just met, the conference organizers, to the conference, of course, to celebrate Vilker. I hope to have some time for questions, but I would like to say that this is a very sensitive and gentle man who's also very precise and rigorous, and it's difficult to balance those things, and I respect that effort that you put into it, you know. And so, yeah, we can just we can leave. This is from a lovely birthday party we had last night that Miguel organized, put a lot of work in, and I see it, and it's a lovely community that you have here, and I'm really grateful to be here.
Thank you very much for a nice talk. So, yes, maybe some people.
If you want to study these this intermittency phenomenon, why don't you just entirely study it in Fourier space on the Fourier modes, and you know that mass of the solution is transported to large K or something like this, or is this visible in the solution that you study for large T?
That's very interesting. I never thought about that before. Well, we didn't look at how the Fourier modes change in time. So I guess that would be the Fourier mode of the solution, and trying to only look at the Fourier modes of the solution. It's an interesting idea. I don't think we've even tried to calculate the actual Fourier modes of the solution. And but so that would be, you would take the Fourier transform of the solution and try to find the coefficients, basically. Okay.
Maybe can you help me to get a global picture of that, what you did? As long as I understand, when you compute only the correlation functions, the expectation values, so all the randomness disappear, and it's only, everything is about integrals of Gaussian functions and the function f that you have, f alpha. So,
Yes.
so that at the end is amount to have everything amounts to prove the convergence of the Picard iterations, and but the G's, they don't have the random component. They are just there because it's the Heat equation. It's just the kernel of Heat equation, and the F encodes all the randomness of the problem. This is correct, where I understood from.
Yes, that is correct.
Yeah, thanks.
So we are out of time, so let's.
Okay, thank you very much.
We resume at 11:30.